Hi, and welcome to this video on proof by contradiction. Now, proof by contradiction is a year 2 topic. You'll have seen previously last year in year 1 we did deduction, exhaustion, counterexample. Those are your proofs in year 1. In year 2 that goes on to contradiction. I've got to be honest, the distinction between the two is not particularly relevant when it comes to your exam paper. If you're doing a full A level, then you've just got to be able to cope with all of them. It just so happens that they decide to put this one into the year 2 content just to, I suspect, just spread it out a little bit. Having said that, the contradiction is a little bit more tricky than the other one, so that's why it's there. But what we're going to do in this video is have a look at proof by contradiction. And this section on infinity and primes and irrationality of roots is something we'll look at in another video. Those are kind of two classic proofs, standard stuff that you need to know. So, here we go. Proof by contradiction. Let's just go through the principles to begin with. So, we've got proof by contradiction works by taking the reverse of your conjecture and proving this to be false, and then working towards a mathematical statement that creates a contradiction. So what we're essentially going to do, we're going to turn it round and prove that the opposite is false. And if the opposite is false, that means the original statement is true. Now that takes a little bit of getting your head around. So what we're going to do is use an example to describe exactly what's going on. So here's my conjecture. If n cubed plus 5 is odd, then n is even. So we've got a statement there, and then we've got this bit over here, which you see popping up a lot in a whole range of different questions, which is normally there for completeness, but in this particular case, it's saying n belongs to the integers, so this symbol here, this Z symbol means integers, but this statement now is absolutely key to what we're going to be doing. It was, in most of the context, it's just a bit of an add-on, but here it's absolutely crucial. So, what we're going to do, first things first, it says we're going to take the reverse of our conjecture. So our conjecture said if n cubed plus 5 is odd, then n is even. The reverse, therefore, is, we're saying that n is odd. And this reversing of our statement is called the negation. So I'm going to refer to that statement now from here on in as the negation of our statements. So, what we're saying is if our negation is true, and we're going to start by assuming it is, then we should be able to write n and the result of n cubed plus 5 as an odd number. This thing here, this 2n plus 1, hopefully you're familiar with that one. So that's just basically an algebraic way of being able to write odd numbers. You can see if we've got, for any whole number m, 2m has got to be even, 2m plus 1 has got to be odd. So those two expressions, 2m and 2m plus 1, are just used to describe odd and even numbers. So there we go. So what I've done is I've written n as an odd number, and I've written n cubed plus 5 as a different odd number. And what I'm going to do now is use these two algebraic statements here to write my negated statement, which is this one, but to write it mathematically. So, therefore, we've got that. And what we're saying there is this odd number here, the blue one, is an odd number cubed, plus 5 equals an odd number. So hopefully you're happy that this statement down the bottom here is the mathematical version of this statement written in words up here. Okay, so that's where we've got so far, and we're saying that j and k by definition have got to be integers as well. So now we've got it written algebraically, we can start doing some work on this, and the first obvious place to start is to multiply out the bracket. So we've got a simple binomial expansion, or however you want to do it there. There it is. And what I'm going to do now is just do some rearranging, and we're going to work towards something that just doesn't fit with what we've got up here. So what can we do? We'll tell you what we're going to do. Let's rearrange it, move the 1 over. Now, obviously there's a plus 1 here and a plus 1 there, so they've kind of cancelled each other out. And then the last thing I'm going to do now is let's just make j the subject and do some dividing by 2. And I've very deliberately written it like that. I've halved all of these terms, and there's half of 5. Now the reason I've done that is because if we've got k as an integer, this bit's going to be a whole number, that bit's a whole number, that bit's a whole number. This bit here, clearly not a whole number. So what we're saying is that j is clearly, according to this, not an integer. And there's our contradiction, because in our definition, we said that j definitely was an integer. So there's no way that j can be an integer, which is our contradiction, which means then our statements, our negated statements, if n cubed plus 5 is odd, then n is odd. That thing there cannot be true because it contradicts our original statement. And so therefore, if that statement is not true, then the one above it, our original statement, is true. And so there we go. There's, excuse me, our proof by contradiction. So what we did, we took our negation, and then we proved our negation doesn't work. And if our negation doesn't work, then our original statement must be true. And there's our proof by contradiction. Right. Hopefully that all made a bit of sense. Let's just go and have a look at another example. Okay, and again, this one, there's a lot of kind of flip-flopping around between trues and falses and all the rest of it, but bear with me. So what we've got here is a conjecture. It says there exists no integers, p and q, such that 18p plus 6q equals 1. Right, now, so our original statement actually says that. Now, note on this one we've got equals 1, which says there's no integers such that it works. So what we're saying is for all our integers, 18p plus 6q cannot equal 1. So there's a kind of slight reversing here, but hopefully you're happy that that thing there is saying exactly the same as that thing there. And here's the slightly tricky bit, because we're now going to reverse that. We're going to come up with our negation, which is we're saying that it does exist. So our negation says there are values in p and q that do exist such that it equals 1. Our original statement says it doesn't. So what we're going to do is prove there's a contradiction within this statement here. And we're going to do it in a very similar way to what we did last time. So if we've got that, do a bit of dividing, and I've divided by 6 here, so we've got 3p plus q equals 1/6. And by definition, since p and q are integers, 3p has got to be an integer, q has got to be an integer, 3p plus 3q are therefore an integer, and we're saying that those things add together to make 1/6, which is clearly not an integer. So we have a contradiction. So straight away that tells us that that statement there, 18p plus 6q equals 1, for p and q being integers, is false because of our contradiction. So therefore, our original statement is true. And it's important that when you go through this, you start off, first step is your negation, then you go for your proof, and then you finish off with this statement at the bottom. If you just leave it here, you're leaving the examiner to do some work, and the examiners don't want to have to do any work. They want you to tell us exactly what's going on, what is being proved by your statement, by your mathematical work. So you need to make sure you put that statement in at the end to get the final mark. And there you go. There's your proof by contradiction. Like I say, to begin with, it takes a little while to get your head around them, but once you get going, they're not actually too bad.